All right, so what are some higher energy orbitals? So if that's the 1s, well, I could jump up to the, what would that be?
2p.
Would that be a 2p? Yeah, 2s. Or it could go to a 2p. A 2p would look like this. You know, this would be a 2p. What would that be? 2p y. Or it could go to a 2p x. Or it could go to a 2p z. And when we look at all three 2p's, one thing we notice about all three taken together, it has a spherical symmetry to it. You know, spherical symmetry. And then on and on. So, you know, an electron in any of these higher energy states would be an excited state. And some people say, well, you know, in the hydrogen atom is a 1s1. H atom, 1s1. And so some people, and I've heard this, I don't know if you think the same, but some people say, well, that means the 2s orbital doesn't exist. You know, hydrogen's a 1s1, so the 2s orbital doesn't exist. Is that true or is that false? Hmm?
Why would it exist?
Why wouldn't it exist?
It's a matter that is not being used.
Right, and so somebody told me that, and then I was thinking, yeah.
But the election that started.
Right, you know, it's not occupied, but it's an allowed state. An orbital is an allowed state of electron, so of course it exists. You know, somebody told me there's no such thing as a 5H orbital, you know, because none of the elements on the periodic table has an electron in a 5H orbital. Is there such thing? HI, yeah. Is there? Yeah, why not? It just because it doesn't have an electron in there doesn't mean it doesn't exist. Okay. So we have potential for a lot of higher energy orbitals. And this is the good thing about the simple numbers. The simple numbers allow you to figure it out. So for example, if I said I want to go to the 99K, if I'm in the 99K orbital, well, does a 99K orbital exist? Well, we got to figure it out. What is K? So that means L is equal to, probably figure it 0, 1, 2, 3, 4, 5. So it goes S, P, D, F, G, H, I, J, K, 6, 7, 8. And so this would be a 99, 8. This is NL. Does that exist? 99, 8 orbital?
Yeah.
Yeah, that exists. Doesn't mean there's an electron there, but it's an allowed state electron, and it's there. And so, how many orbitals are there in the 98K? We would call this the 99K sublevel. How many orbitals are in that sublevel?
99 squared.
That would be the level. There would be 99 squared orbitals in that level. How many are in this sublevel? There would be 99 sublevels with n equals 99. That's true. So there's 17 orbitals. That's right. What are they? They're the -8, -7, -6. Exactly. That's it. And so we got a lot of orbitals. We can figure out which ones are allowed and which ones are forbidden. And the allowed ones are allowed, so they exist as allowed states with electrons. All right, we're going to continue talking about this. So let me bring up the periodic table. For figuring out what the ground state is, you know, we have exceptions. And you remembered two of the exceptions, right? One exception for the ground state, which was a little different than what you predict because it violated off-bow, is chromium. But it doesn't really violate off-bow because there's an energy compromise there. Another one is copper. And so we could say, you know, members of the same family are going to show similar. Yeah. So we know those, but there are other exceptions as well. You know, especially when you get to very high ends, what happens to the spacing between the orbitals? It gets smaller, so the exceptions are easier. It isn't so difficult to promote an electron to a higher energy orbital when it's just a tick above. You know? And so what we often do is we use the periodic table to help us figure out these electron configurations. You know? And so you'll see different styles of periodic table. Like, for example, here, if we're looking at lanthanum, then the periodic table would be, and this does it according to shells, right? In the third shell, what are the set of orbitals that we have in the third shell? We got the 4s2, followed by the 3d. 10 of those, and 10 electrons, and then the 4 p's here. And so, based on the periodic table, we can tell. In the next shell, what do we have? In the next shell, we got the 5s, the 4d block, and the 5p. That constitutes the fifth shell. In the sixth shell, what do we have? We got the 6s2. And then here, we got to drop down to, because there's not enough room to insert it here. And so we go 6s2. This is the F. This is 4f. The 4f can hold a total of 14 electrons because there's 7 orbitals, each orbital holding 2 electrons. So we go 6s to the 4f to the 3, 4, 5d to the 6p. And so that constitutes the next shell here. And so there's some interesting things sometimes about these shells. One thing is how many electrons does the shell hold? And so if you look at the first shell, it only holds 2 electrons. The second shell holds a total of 8 electrons. The third shell holds a total of 8 electrons. The fourth shell holds a total of 18 electrons. Out of those 18, does that mean, you know, all of them are valence electrons? No. What are the valence electrons in the fourth shell? The valence electrons are the highest end, so we got 4s and 4p. And so to fill the valence shell in the fourth shell, this is getting all mixed up. How many valence electrons does it hold? 8. In other words, to fill up all the valence orbitals in the fourth shell, how many electrons do we need? 8. And so there's the octet, right? To fill the entire shell, we would need 18. Is 18 electrons stable? Yes. 18 electrons stable because not only have you filled the
Uh,
4, n equals 4 valence, but you've also filled the 3d subshell, which is stable. And so, 8 or 18 electrons is a stable number. And so they have something called the 18 electron rule, but do you really need the 18 electron rule? It just makes sense that if you fill, or do you really need the octet rule? Yeah, I guess it helps. It helps to remember. And so the 18 electron rules, if you fill this, of course it's going to be quite stable. And so this would take 18 electrons. What would the next shell take to completely fill 18 electrons, of which 8 of those are considered valence, right? 10 of those are considered subshell core electrons. Does that make sense? To fill the next shell is going to take a lot more electrons because we got
14.
these 14, so that would be a total of 32. So, all right, this is one type of periodic table. So let's say I want the electron configuration. Oops. I want the electron configuration of you guys remember electron configuration?
Yeah.
I want the electron configuration of uranium. What is it?
Whoa. Can we abbreviate by the noble gases?
Yeah, we could abbreviate by noble gases, or we could just go down. It's not difficult if you have the periodic table here because it would just be 1s1,
Yeah.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then 56, we drop down to 57 here. 4f14, right? 5d10, 6p6, 7s2, and then we drop down. Oops, my computer. 5f1, 5f2, 5f3, 4, 5, 5f4, and we stop there, right? And so we could do that, or we could use Nobel gas abbreviations. What would be the nearest Nobel gas? Well, this is element 92, and so it would be this one, the last one, radon. Radon is an interesting noble gas because normally you think of noble gases as being inert. But radon is chemically inert, but unfortunately it's radioactive. Yeah. And so what radon does is when it decays, it emits alpha particles, and alpha particles are very safe. They're a very dangerous form of radiation. This is a very dangerous form of radiation. Like, for example, alpha particles are dangerous because they are powerful. Somebody remember? Somebody told me. Who told me about alpha particles? Arthur, was that you? No? Remember when we were talking about oxidizing agents? Was fluorine the most powerful oxidizer you've heard of? No, you've heard of a more powerful oxidizer. What was it? I didn't outright state. This is, I think I did. I think at one time I said it makes fluorine look weak, something like that. What is it? Nucleus of a helium atom, which is called a alpha particle. Alpha particles are much more reactive. Well, anyway, alpha particles, what do they want? They want electrons. If they take electrons from your DNA, is that a good thing or a bad thing? It's a bad thing. And so they say that, if alpha particles hit your skin and cause DNA damage, it's okay because your skin gets DNA damage every day from UV radiation. And so you have the repair enzymes in your skin. But the problem with alpha particles is not skin contact necessarily, but the problem with alpha particles is they're gas, radon is gas, and you inhale it. And then they take the electrons and cause DNA damage to your lung tissue. But does your lung tissue have that?
Regeneration.
Yeah, does it have the repair enzymes that your skin has? No. And so it doesn't repair itself. And so that's a problem. Alpha particles will cause.
Possible lung cancer.
Yeah, exactly. Radon, radon's around here. You can look at a radon map, there are places where there's a radon emitted. Usually, in granites, for geologists, you learn about this. There's uranium trapped in a lot of granites, and uranium, eventually, some radon's generated from that, and so houses should have good ventilation so that the radon doesn't get trapped inside your house. Up in Palos Verdes, all the schools test kind of high for radon, and so they put in some ventilation in there. You can buy radon home test kits too, if you're ever curious. But I think around Torrance is pretty low. The radon, beach cities is very low around here. It depends on what the sediment of the soil is made up of. But you got to watch out for radon. But anyway, radon is element number 86. And so the other option is, this is a lot less writing. We just go radon. We put it in brackets like this. And then from radon we go, what's this? 7, was it 7s2?
Yep.
7s2, 4f, 4. Well, that wasn't too bad. Oh,
Is that 5?
5, yeah, they were right. 4, 5. This is 5f4. Thanks. All right, this is one style of periodic table to make your life more difficult. We're going to look at another style of periodic table. All right, look at the periodic table behind us here on the wall. Okay, let's follow the numbers and then do uranium as well. Yeah, we're going to do uranium again. Okay, but we're going to start at radon. Read it off for me from radon. Radon's over here, 86. So 87, 88 would be 6, 7s, 7s2. Then we have to go to 88 goes to 89. But where is 89? 89 is, can you guys see it? It doesn't go to F. 89 goes to D. 3, 4, 5, 6, D1. Right? And so when we look at our periodic table, it goes radon, 6D1, 4F3. 6D1, 4F3, isn't that bizarre? Which is one electron plops into the D and then the remaining 3 go into the F. Do you see that?
No.
Okay, we're going to go through it here. So we're going to start with radon, and then we're going to go to francium here, which is 1, 2, 3, 4, 5, 6, 7, S1, 7S2. That's 88. See that? Where's 89? The next one. This is in the D block. 3, 4, 5, 6D, 6D1. But you look over here, that's 104. And so we go from 89 to 90. And so 89 to 90 means we go 61 to 4F, not 4F, 5F, 1, 5F2, 5F3.
So you put 4F.
Okay, I did it again. This is 5F3. 5F3. All right, so why do we have two different electron configurations and two different periodic tables? Can somebody tell me why? Actually, both of these periodic tables you'll find online. Let's see if I could find some more.
Is it more than 2 types or just 2?
No, basically just two types. Here. No, that's not it. So why are there two types of periodic? What do you think? You know, there's a reason for that.
One is more updated.
One is weird, the other seems normal. No, both. You know, it depends on the author. You know, so it depends on the author. Like, for example, look at this. Do you see this periodic table? This is like that periodic table, right? See if I can get. This is the American Chemical Society Middle School Chemistry periodic table. So the middle school chemistry table looks like ours, which is 7s2, 6d1, 5f, 1, 2, 3. What's going on with all these other tables? Well, some people don't like this because it's messy, and so they try to clean it up and make it more organized or orderly, right? That's all.
Is it just 15?
Or do you just have to?
No, F is not 15.
You still count it as the D1.
Notice the position of uranium in the F. Notice the position of uranium here in this F. It's not going to make F 15. Notice the position of uranium here. Do you see the difference in the position of the uranium?
Yep.
And so the F is still going to be 14, either periodic table you use. All right, so basically it boils down to this. Did you come up with an idea? You know, this happens a lot in science and other fields. It's like, you know, some people will say making assumptions and simplifying things is often done, right? And so here, some people say, you know, what's the big deal? This is more accurate, of course, but it's less clean. Let's just clean it up, make it a little less accurate. It's not going to make that big of a difference. That's the philosophy. So that's like, you know, when you're doing chemical reactions, you're predicting single replacement. Single replacement can get messy, you know, the A plus BX pattern, because it doesn't always work. And so we're going to clean it up. We're going to clean it up. We're going to just ignore all the messy ones and just do the nice ones that work, right? And so this is kind of the same thing, the same kind of philosophy, and you see it often. You see it like in Chem 4, they don't want to do the messy ones because there's not enough time to talk about the messy ones. But the problem is they should mention that there are messy ones that don't fit this pattern, right? And so the pattern could fail. That's the problem. That's perfectly fine as long as you state that, right? And so something like this here, what's our book? What do you think our book is going to have? Our book has the nice, clean one. Okay. And so either periodic table you use, but you should know that there's a little bit of conflict here. You know, some people are saying that it's going to be 7s2, 5f4. Some people are saying it's going to be 61, 5f3. Which one do you think is going to be correct? the one that agrees with experimental fact. Right? And I would think this one's probably agreeing with experimental fact, because how else would they know it goes 61 and then 5F? Why doesn't it just go straight to the 5F? Right? But anyway, just realize that sometimes things aren't always as clean as you'd like them to be. Okay.
The next one made it later.
But whatever periodic table we have, if I asked you the electron configuration for like uranium, you would just use, if I gave you this periodic table, you'd probably say 7s2, 5. If you use the periodic table up there, use that. And then what would I do? I'd have to count them both as correct. All right, that's electron configurations. And then what else do we have in Chapter 8? I think that's about it for Chapter 8. And so we're going to
Can you do like practice problems
practice problems in Chapter 8?
the things that you would consider for the test? We should have it next week or today.
Oh yeah, we could do some. You want to look at some practice problems?
Yeah.
All right.
That's solidified. We have to What? I think you can.
Can I see your cookie? Can I see your cookie? Oh, that's cool.
It's my wallet.
I used to have that. What's really that? I'm afraid of people get stolen.
Yeah, what about like you?
I don't lose my phone.
It's a power.
And then it
I
happened.
always, if I don't find it in my pocket, I'll just finish with my like my
Okay, this site is.
sometimes in my pocket. You know, just
Okay.
For the first part of the chapter, where you have like equations, you have like Planck's equation, like
Planck's.
the energy Planck's equation, like the energy of a photon. Are we responsible for those?
Yes.
Also, like the delta E.
Yes. So, are you responsible for those for the test? Yes.
Do we have to memorize them?
Do you have to memorize them?
There's a
No.
constant, H constant.
No.
No.
No. Those you don't. Don't worry about those.
I'm
Okay.
trying to see what I have.
You do have to memorize the equations for Chapter 7, but not for Chapter 8. Chapter 7.
Like delta H, delta E.
Right.
kiss on me.
But not for chapter 8.
Not for Chapter 8.
So E, well, it's just.
Well, it's something at this Mastering Chem page is not coming up, so I'm just going to read the problems. You have your book?
You just take a number.
You know what, though? The problems I want you to do are the homework problems. You know, those are good ones to review. But let's take a look at some of the. You want to go through the integrative advanced exercises? Let's do that. And so we could take a look at. But before I do that, how many people have done number 90, Chapter 8?
We're not there yet.
Nobody? 92? Or 93? 101? 102?
I was waiting for the lecture to be done.
I'm sorry?
I was waiting for that for the lecture for chapter 8 to be done.
Just start the homework? All right. Well, there are different things you could do in preparing for the exam. It's too bad this thing's not working. Number 90, electromagnetic radiation can be transmitted through a vacuum or empty space. Can heat be similarly transferred? Can heat be transferred through empty space?
No.
No. Right, heat requires a medium. What you're doing in heat is you're transferring from high kinetic energy to low. So if you touch a hot metal surface, right? I mean, if I held my hand out here, am I going to get burned by the hot? No, I'll probably feel the heat. I'll feel the heat because either this is radiating infrared or it's exciting air molecules. But since air is a lot of empty space, I don't have to worry about getting severely burned, even though this is hot. This could be very hot, right? But if I touch it, then I have to worry about getting severely burned because all of a sudden, all the kinetic energy of the metal atoms will be transferred to the molecules in my skin and excite those and cause damage, right? And so if there was a vacuum separating this from my hand, the only way I can feel the heat is if it were infrared, you know, infrared radiators. This is why, you know, I was at the barbecue shop the other day, and I guess, you know what happened is the patent on those IR, have you seen those IR emitter burners? The patent ran out, and now everybody has these IR burners in their barbecues, and I thought, wow, that's pretty interesting. I want to get one, actually. I was thinking of getting one, but it cooks differently because, you know, an IR is going to heat things up faster because a normal burner relies on like convection or heat conduction, you know, where you got to heat up hot air, and the hot air is going to cook your food, right? But an IR burner just is irradiation. You know, and so you're just irradiating it with infrared, and infrared travels at the speed of light, and so I was thinking that's very cool. And it's much more efficient, you know, in heating things. It's like a microwave oven versus a stovetop, you know, kind of thing. I was thinking, you know, as an analogy, but not a perfect analogy because you aren't hitting the resonance frequency. But you know, you are microwaves are quite a bit more efficient. Well, anyway. So the answer to this is no, heat cannot be transferred through empty space. Heat, technically the definition of heat is, you know, transfer of kinetic energy from a hot object to a cold object. You can heat up things using infrared radiation because infrared, what does infrared radiation do to matter? It excites what? In what manner does it excite the electron? It excites the electrons in... it's hard. It excites electrons in metals easily because metals are loosely held, but electrons in molecules are a little bit harder to excite. And so rather than exciting the electrons, it excites the... It excites the polar bonds, which causes do you guys review this? When we first to day 1 of chapter 8? Remember to review every day is always good. Review every day to make it stick. It causes vibrations. How does it cause vibrations? You got a positive end of the bond, a negative end of the bond. You got the electric field, you're going to start causing a vibration. Did you know vibrations are quantized? You know, you think, oh, I'm just going to vibrate that a little bit. No. You have to vibrate it at just the right energy. Otherwise, it won't vibrate, you know? When it vibrates, it's called the resonance frequency for the right vibration. You know, there's a very famous video of the Tacoma Narrows Bridge. You know, all these waves passing by in the wind. It doesn't absorb anything until it hits that right vibration frequency, and then, boom, it starts to vibrate or oscillate. Have you seen that?
No.
That's a physics. You haven't seen that? Maybe you want me to show that?
Yeah. The. Oh.
Same year.
Oh my god.
See if they're in the audio.
Is that the wind?
Yeah. See, right?
No.
These things are quantized, and so you know this only absorbs certain energies, right? There are forbidden energies that it absorbs, good, and allowed energies. And the Tacoma Narrows Bridge after this. Ooh, lone car left on span. It's been years. The last time I saw this video was in physics.
Where's the car?
I guess that's it.
This clicking?
That would be fun if it would break.
If it didn't break.
If it didn't break, it would be
I would be
fun.
freaking out.
Wouldn't that? My God. That would be a crazy roller coaster or something. Oh wow! Wouldn't I should patent? You know, I want to patent this now. The crazy resonant frequency roller coaster ride.
Oh god.
It's the rear.
What is that?
This is vibrating. It's oscillating. Do you see that?
How can the wind do that? It doesn't even look like.
What state is this?
Washington.
I'm not going there.
Stay away from the bridges.
Just
Oh, there's somebody inside the car. The dog in the car. Or Dawkins? Is that dog or dog?
the dog alone. That's why they would bring it back. Wow.
Wow.
Is that him?
I think so.
Where is he?
There.
Yeah, he's walk-off.
Why is that? Who's walking?
Is he the guy?
Does the bridge flood?
He's trying to stay in the yellow line.
He's
Trying to walk in.
like drunk.
I'm drunk, guys. Okay. Poor guy.
Wait, he's just
Where's the
like
dog?
chilling.
God, he should try to save his car.
He's like, I forgot the dog. The car doesn't move. Would it collapse?
Yeah.
How long is this video? I saw the condensed version. Okay, I'm gonna fast forward a little bit. Oh, that fast forward is too far. I ruined it. Sorry. That's what.
Oh my god. That is good.
So do you know what they do now?
They fix it.
They measure they measure the absorption spectrum of the bridge to see at what energies or what frequencies or what wavelengths it absorbs at, and they make sure that nothing can approach that, so it's all forbidden. And then when to make it, do you see what? And so they totally change the way they design it. And the way they design it, how do they measure the absorption spectrum of bridges? One way that they do it for the old bridges is they go over and give it a big pulse of energy, a big short pulse of energy, and then they can use a spectrometer and measure what energies were absorbed. And so they can see that it's quantized, just like everything else is quantized, right? But here, here's a macroscopic object, and so you see that this is actually quantized.
When would it win?
But the right,
The right frequency of
The right frequency will cause this to begin to oscillate. It's just like infrared radiation.
What year this is?
What year is this?
Yeah.
I don't know. I don't know.
1940.
1940.
What else could it be though? That's what I'm asking. If it's not.
You don't want to watch it? I don't know if this is a good one. Let's see if this has some good animations of vibrations. Water molecules are, the vibrations of water molecules are quantized also. The water molecules can only vibrate with certain frequencies of light, just like the bridge, you know? And so the IR spectrum of a water molecule, you know, what energies or what frequencies or what wavelengths of light are absorbed by a water molecule are quantized. They're forbidden energies and allowed energies for the vibration. So there are three. Actually, there are only three vibrations for water molecules. So if you're heating water on the stove, most of the energy is not absorbed from the flame. And so heating water with a flame, okay, let's say you're pumping in 3,000 kilojoules into that water. How much of that 3,000 kilojoules is actually absorbed by the water? Well, how much depends on, you know, what the spectrum of that energy is. That is, you know, what that energy range. Well, anyway, getting back to this. So, you know, these are the three types of vibrations that are allowed. There are no other vibrations allowed for water. And so the water molecule, when you look at the infrared spectrum, there are only three peaks. Everything else is forbidden. So, let's see with the infrared spectrum of water. Although it's pretty broad, you know, because they're. It's not supposed to be. I want one of these. I want to get one of these for the department. But anyway. Yeah. Anyway, I'm in the wrong. I need to be included. Do you want to see it or not?
What?
The IR spectrum of water.
Yes.
In infrared spectroscopy, they do the peaks differently. The peaks are inverted, and so normally what we think of peaks are actually valleys. And so this is one absorption band here. Don't ask me why they do it this way. It's just historically been done this way. And so it's absorbing this range of wave. These are called wave numbers. Wave numbers is energy. And infrared spectroscopists have historically used wave numbers or microns to describe it. So this is one absorption band. This is another absorption band. This is another absorption band corresponding to those vibration. And since water, water, if it were single, okay, if you had a single water molecule in empty space, a single water molecule in empty space would give you sharp absorption lines. But water molecule doesn't sit out in empty space. Typically, water molecules surrounded by a whole bunch of other water molecules, which screws up their vibrations sometimes, right? And so we get these kind of messy bands, rather than sharp, clean lines. Does that make sense? So this is typical for molecular spectroscopy. Anyway. That's that. Let's go back to problems here. So to simplify, IR, what does IR do? It causes those vibrations. Right? And so an infrared, you know, you got an infrared barbecue, the infrared radiation's hitting it. You know, and it's a broad spectrum infrared emitter, so not all that infrared's being absorbed though. But in meat you have lots of different things like water, protein, fat, carbohydrates. So it could absorb a lot because there are a lot of different vibrations that you can have in there, and so therefore you can heat up the meat quite quickly. 92. Infrared lamps are used in cafeterias to keep food warm. How many photons per second are produced by an infrared lamp that consumes energy at a rate of 95 watts and is 14% efficient in converting this energy to infrared radiation? Assume the radiation has a wavelength of 1525 nanometers. That's number 92. Number 93, in 5.0 seconds, a 75-watt light source emits 9.91 times 10 to the 20 photons of a monochromatic single wavelength radiation. What is the color of the emitted light? Okay, so 92 and 93 are very similar. It's just working with photons, total energy, and photon energy. Remember, we have two energies. The energy of the photon per joule and the joules per mole is 1, but that's similar to joules per photon. It's the same ratio. There's another energy. You know what? Because maybe it would be more effective if I wait a little bit so that people have time to just go back through their notes or skim through the book, and then we'll cover these problems. We'll cover these problems on Monday. How about that? Okay? We'll do that then. And then, so take a look back through, you know, about we have two energies, and that's really important for 92 and 93 that we got to deal with. 101 is ozone absorbs ultraviolet radiation and dissociates. This is two energies also. Here would be in moles per mole as well. 102 is radio signals. Okay, for orbitals, you know, what do you need to know? And let's see if I could get mastering Chem to turn off. Let's try a different browser. Actually, let's take a break. Let's take a break. Let me see if I can bring this up. We'll take a break for 10 minutes, and then this came up, so I'll get it up. But let's go ahead and still take a break for 10 minutes, and then we'll look at some of the other problems.
No, it's just a cool hat. Oh, I got this in Chicago, actually.
I know that one, but where was this one?
the middle of water.
So then we go down to.
Nani?
Yeah.
Normally, that's it. That's how it goes.
Yeah.
Yeah.
Yeah. Like, what is this piece? This one would be 7. Yeah. Oh,
Yeah.
so like with these, it's a word number. So it would be C and then this one's right. Okay, so that would be uranium. So then for this one, oh, so is this the same? This is so these two things. So which one would you want us to? Yeah. Oh, yeah. I think we get like yeah. Oh, sure.
Where are you gonna go?
What's gonna hide? What's gonna hide? And then so you move right there. Where's gonna be? Over here? Oh, all you need that glory on. Yeah. Who else? These two. So, RS, is and then you got what is this? Stop! 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 You're laughing about like you're not I need more than that. That's what dude, we can the champion. What do you know? I can't get how'd you get the peanut butter from? Where? Really? Is it? Who's this? What the heck? Oh, I thought you meant
So we haven't What about the